All right, ladies and gentlemen, today we are going to dive into the first part of 1.3, which identifies our 12 basic functions. If you are at home and you normally do not print out the notes, I highly recommend printing out the notes here, as you're going to want to have the 12 basic functions handy for you. If you are in class, the notes for 1.3 are on the top of the computer cart. So if you want to go ahead and grab a note from 1.3 from the computer cart there. But the ultimate goal of this section is to be able to recognize graphs of 12 basic parent functions, determine domains of the functions, and be able to combine the functions in various ways to create ultimately new functions. And so let's kind of define that term parent function first and foremost. Parent function just means it's the most original basic version of the function. Your best example is y equals x, right? It's a line that goes to the origin. It is your parent function before any slope has really been changed and any real y-intercepts have changed. Same thing for y equals x squared, y equals x cubed, y equals the absolute value of x. All of those are part of our 12 basic parent functions. And that is what each of the next handful of slides are going to represent. Now, I am not going to necessarily go through every single one of these. You are just responsible for making sure you know what these are, and we'll be doing enough practice with them over the next handful of days that hopefully you guys will be good to go. So we have our y equals x, that is our identity function. We have our squaring function, which is our first quadratic. We have our cubing function, and then we have our reciprocal function, in which you have 0 in the denominator. And so that's why we would have a asymptote, as you see right here at the y-axis. Our next set that we're going to take a look at is our four new functions. We have our square root function as a basic one, exponential function, which we have the number e. It's an irrational number raised to x. Basically, that e is a symbol that is used for a number that's roughly around 2.71. And the reason why it's an e is for Leonhard Euler, who was kind of dubbed as the individual who has made e a popular use of a symbol here in our mathematics. Natural logs. So we're going to talk about natural logs. You should remember natural logs from our discussions in Algebra 2. Here's our natural log function in its basic form. Again, you can see where you cannot have the natural log end up being that 0 value, and so you see why you have a asymptote there at y equals 0. You have your basic sine function, which we're going to do a deep dive into graphing sine and cosine functions. And then we have on up here, of course, the last four, which is our cosine function, our absolute value function, the funkiest looking one, which is called the greatest integer function. It's also called the step function. What's very interesting about this function is you can kind of see here, look at all this jump discontinuity. It looks like there's a bunch of non-existent points, but believe it or not, this has all of the values, the integer values for y. It may be non-existent down here with this open circle, all right, but then it picks back up again with this closed circle. Open circle, it picks back up again at this closed circle, and so it's kind of interesting. The range there has everything to do with the idea that there's a bunch of jump discontinuity in this function, and it's a very interesting one to look at. And then the last one is our logistic function, probably the one that we talk about the least is our logistic function. You can see the basic of it down here. I guess what the biggest part of the logistic function is the fact that it's always going to have two horizontal asymptotes. So it's a completely bounded function, as is the cosine function, as is the sine function. And you're going to find, at least to get started off with, you're going to have the x-axis and y equals 1 as being your horizontal asymptotes. And then obviously that will change if you increase or decrease the function vertically. Okay, so that's a brief upload, or I guess up to what you can expect there. So what I want you guys to do here at this point is go ahead and pause the video and give this guy a shot using the 12 functions below. Answer these 5 questions. you can talk with somebody that's next to you if you want to, but you can just work on it on your own as well. Just remember, stay seated in your own assigned seats and no moving around seats. But if you want to ask somebody that's next to you, that's fine. So go ahead and pause the video and see what you come up with, and then I'll reveal the answers. All right, so hopefully you can take a look at here. So the first question says two of the basic functions have vertical asymptotes at x equals 0. Which two? All right, so hopefully you found that y-axis being a vertical asymptote for our reciprocal function 1 over x, and you found it for our natural log function there. So let's go ahead and take a look at those real quick. For our natural log, you found our vertical asymptote at the y-axis, x equals 0, and then also for the reciprocal function, which we talked about in the beginning of the video, it's going to have vertical asymptote at the y-axis, x equals 0 as well. The next one says form a new function by adding these functions together. And does the new function still have a vertical asymptote at at x equals 0? Well, if you think about it, f of x, if you literally just added these two guys together, you can check on your graphing calculator. But remember that because this 0 is still here in the denominator, and the fact that this natural log of x can't equal 0 anyway, of course it's going to still have a vertical asymptote there. You're still going to take into account that domain. Number 3, it says 3 of the basic functions have horizontal asymptotes at y equals 0. So you can just, again, you're just analyzing those graphs there. Of course, we also saw the reciprocal function had a horizontal asymptote at y equals 0. So that's our reciprocal function 1 over x. We also saw that we had one for the exponential function e to the x. And then we also had one to finish up for our logistic function of 1 over 1 plus e to the negative x for that logistic function there. And again, you can always just go, again, you're just going back to that graph, taking a look at where you find your horizontal asymptotes. In this case, they wanted the x-axis, and you can kind of see where those are going to be. And then it says form a new function. By adding all of these guys together, will you still have one? So I'm not going to rewrite all this out, but you literally just add all these together, just put an addition sign like I did up here, and the question would be, would you still have one? And the answer is still yes. You're still going to have the same quote unquote issues, if you will, if you added them together. And you can literally just put in your graphing calculator to double check and see if you are going to actually have those. So yes, you are still going to have a horizontal asymptote there. And the last one says if you graph the functions 1 over x, g of x equals 1 over 2x squared minus x, and then h of x is the combination of both of them, it wants to know, does h of x have a vertical asymptote at x equals 0? And so this one's kind of interesting here in this case. So let's take a look. So if you actually combine these two guys together, you get h of x, and actually add 1 over x plus the 1 over 2x squared. So if you graphed this function, you might be thinking, well, of course it's still going to have a vertical asymptote at x equals 0 because of this issue right here. Well, we have to be a little bit cautious on this one. Reason being is because if you look at these two fractions, you actually can go ahead and add these two fractions together. Let's get common denominators and add these two together and see if there's still going to be a vertical asymptote there. So if I were to multiply this denominator of x by the common denominator in this case here, which would be 2x minus 1, let's go ahead and I'll show that for you guys. So if I factored out an x, I had 2x minus 1. All right, to get common denominator, I multiply this x by 2x minus 1. And I'm running out of room here, but I would get 2x minus 1 plus 1 over 2. Sorry, I'm running out of room here. Over x times 2x minus 1. And in a second, you'll see maybe why I went ahead and left this x out here. Because look what happens. The -1 and the +1 will cancel out. And so that makes 0. But look what cancels in the numerator and the denominator. X and x. So we actually would not have vertical asymptote at x equals 0. We would have removable discontinuity at x equals 0 there. So it's kind of interesting in that case. And again, you could have graphed it to kind of see exactly what was happening there. But interesting in that case how it differed from the previous one in number 3 and in number 2. All right, so let's go on and take a look here at a couple of examples for today. So it says looking for domains. What you're going to be looking for here is looking for the 9 of the functions that have the domain that is the set of all real numbers. And so your domain is from -infinity to infinity, and says which 3 do not. And so again, I challenge you to pause this video because most of this can kind of be practice just for you guys to look at the functions and then come back and see which ones actually, follow these guidelines that the questions give you. And so I challenge you to pause the video and do part A, B, and C before you look at my answers. All right, so for part A, so which ones go from -infinity to +infinity for our domain? All right, well, the very first one, of course, we see is going to be the function f of x equals 1 over x. That's going to be our reciprocal function. You're also going to see a square root of x. Nope, I'm looking for, oh, no, never mind. I'm right. It's asking which 3 do not. Thought I was looking at the wrong problem there. I'm doing the right thing. And f of x is the natural log of x. So the question here said which 3 do not. I was wondering what I was like, that doesn't make sense, but it was asking which 3 do not. So in this case here, if you go take a look at the functions 1 over x and square root of x. So here's our square root of x function. Clearly, we do not have anything in the negative, so it does not have a domain of -infinity to infinity. Okay, here for our 1 over x function, our reciprocal function, we do not include 0 in that domain because of the vertical asymptote that we have there. And then likewise for our natural log function down here, we do not include 0 or anything negative for that matter, so it does not have a domain of all real numbers. Part B, it says one of the functions has a domain, the set of all reals except 0. Which function is it, and why isn't 0 in the domain? And so in this case here, we're looking at y equals 1 over x, all right, or our reciprocal function. And again, that's just because it is undefined, of course, at 1 over x, or when 0 is in that denominator. So it's going to have a vertical asymptote at x equals 0 in that case. And then the last one for part C, it says which 2 functions have no negative numbers in their domains? No negative numbers, and we've seen that in our last one. All right, our last one, we've seen that we cannot have a negative number for the square root of x, and we cannot have a negative number for the natural log of x. Okay? So hopefully we did okay there. And again, as we move on to our next video here, I challenge you to pause the video, try it first, and then come back and see how you did once we discuss them. So this one says only 2 of the 12 functions have points of discontinuity. So there's breaks, holes in the graph. Are these points in the domain of the function here? And so let's first and foremost kind of talk about which one has quote unquote the broken graphs, right? And so the broken graphs, remember you have to lift your pencil up if you trace them, is your 1 over x, your reciprocal function, and your step function, or your greatest integer function. Like literally it's a step. And so in this case here, what's interesting about f of x equals 1 over x, okay? It says, are these points in the domain of the function? And so obviously for f of x equals 1 over x, right? You have a vertical asymptote at x equals 0. And it says, are these points in the domain of the function? Well, no. So this is kind of a strange problem, I guess, here, because you could technically say 1 over x is continuous over its domain. Now, it's not a continuous function altogether, but if you're talking specifically over its domain, it is continuous. So if I look at the function here, I can trace over this part and not have any holes or gaps because that's part of the domain. And I can trace over this part here and not have any holes or gaps because that part is part of the domain. Altogether, it's not a continuous function. Okay? However, we could classify it as continuous over its domain because this part right here at x equals 0 isn't a part of the domain anyway. And then going back to the other part of the question, all right, for the function, the step function or the greatest integer function, this has, of course, jump discontinuity. Well, where? The greatest integer function, all right, will have jump discontinuity at every integer. All right, so literally every integer it's going to have jump discontinuity, but it's kind of interesting if you look at this function. It looks like you might not have a domain of all real numbers, but believe it or not, you actually do, right? You have this point included, and then all of these numbers in the horizontal line, those are all the decimals from -5 to -4. And then it picks back up again up here at -4. It doesn't exist at -3, but all these decimals in here, it does. And then so on and so forth as it goes through. So it's a very interesting function with its domain. And then let's look at two more before we get out of here for the day. Let's look at boundedness. It says 3 of the 12, and again, I challenge you to pause the video to try it on your own before you listen to my answers. 3 of the 12 basic functions are bounded both above and below. Which are these 3? Okay. Well, remember that means it doesn't go to positive and negative infinity for the y values. And so here is going to be one of our bounded functions, our logistic function. We have our cosine function, and we have our sine function right here. So we have our cosine function, sine function, and then we have our logistic function because it does not go to positive or negative infinity for the y's. All right, and then the last part of part 1 is going to be looking for symmetry, So again, pause the video, give it a shot on your own, but it says 3 of the 12 basic functions are even. So remember, even symmetry means they have axis symmetry. Axis symmetry. All right, so specifically y-axis, they're all going to correspond to y-axis symmetry. So which of the 3 are even functions here? All right, well, the first one that we're going to take a look at is our absolute value, right? You split it directly in half at the y equals 0, x equals 0 at the y-axis, and it is the same thing on both the left and right-hand side for the absolute value. We are also going to see that in this case here at the squaring function, or our quadratic, of course. And then the last one that might not be quite as obvious is going to be our cosine function. If you take a look here at the cosine function, split it right between at the y-axis, it's the same thing on the right side as it is on the left side of that graph there. So you have your absolute value function, you have your squaring function, and your cosine function. All right, and that is going to wrap it up for this video. Of course, you can go ahead and revisit any of these problems if you need to, but by rewinding it. Before you get out of here for the day, please make sure that you complete this problem here into this tiny URL that is going to be part of your employability for today to make sure that you are a part of the lesson and watch the videos.